Okay, I'm going to go through this lecture on vector algebra, lecture 3. Let's see where we're up to. We're up to vector multiplication, scalar product, rules of scalar product, power of vectors, perpendicular vectors, and then we're going to look at some examples. We're going to see that there is a second type of vector multiplication called a vector product, but today we're just going to look at the scalar product. So the learning outcomes for today, we're going to be able to multiply vectors using the dot product, or also called the scalar product, use geometric and Cartesian components of the dot product, find angles between vectors, find components of vector along an order vector, and solve some simple engineering problems. Okay, we're going to do a little recap here. We've got two vectors, position vectors for A and B in a plane. We can do A plus B. This is the vector A to B, but the black line here shown is minus B plus A is AB. We can see all this in 3 dimensions, but what we really want to see on this diagram is how we add two vectors together. Well, that blue vector A could be moved to this blue dashed line here, and then we have B and A there, and the line joining the two is B minus A as well. And the parallelogram law, we can draw the parallelogram and close the diagonal with that line. There it is in components for three vectors, 3 dimensions. What we're going to look at today is vector multiplication. Now, there are 2 types of multiplication for vectors defined. We're just going to look at this one I've got here second. We've got the vector product and the scalar product. We're going to look today at the scalar product. There it is. The scalar product is also known as the dot product, or it's also known as the inner product. Now, I will use the term scalar product and dot product interchangeably, and you'll see why it's called the dot product in a moment. One thing that's the dot product is particularly useful for is to find the component of a vector in a certain direction. So if we see that line A at an angle theta to the axis, what we'll call the OP axis, the component of that vector A along that OP axis is clearly A, the magnitude of A cos theta. And that's what we could call ON. So this is actually our definition of the vector product. It's going to be this A cos theta. However, we're going to see some more details of how we get to that, and it'll be a bit more clear. We can relate work done by a vector along another vector. So if force is represented by a vector and we have a direction along which a body moves due to that force, we can use the dot product to calculate the work done. So this is a typical application of this mathematical idea of a scalar product, a dot product. The definition of work is the amount of displacement along the direction of applied force. We can compute the force, the component of the force in a particular direction, and then multiply it by the distance moved. So OA, or A, is the force vector, and length OA is the magnitude of the vector A. the work done is force times displacement, so we'll see that we can do this calculation to get the work done. And it turns out that this is a geometric definition of a scalar product between two vectors A and F. We would do A magnitude of A magnitude of F times cos theta. Okay, we'll see more details of how this is done. So consider three vectors that form a closed triangle. Right, we see this. Clearly, C, which is going from this top point here down to this lower point, is minus A plus B, or B minus A. We can look at this in terms of the cosine rule. So for any triangle, we've got this cosine rule, which you're aware of from your previous math studies. Let's apply this cosine rule as though we've got these two sides A and B of a triangle, and there's our vector C. So because the cosine rule is really working in terms of magnitudes, we can write the magnitude of C squared, magnitude of A squared, plus magnitude of B squared minus 2 magnitude of A times magnitude of B cos theta. Now, as these two vectors have components, our magnitude of A all squared in component form is A1 squared plus A2 squared plus A3 squared, and similarly for B. So we've got those two, and we can substitute them into this cosine rule. It starts to get a bit longer once we expand. For A minus B, B minus A is that, and we're going to see that used in the next slide. We can rearrange this whole thing, because really, look at this, we're interested in this bit, which is our definition of the vector product, the dot product, sorry, the scalar product, the dot product. So expanding all of this, we'll see that we've got B minus A there, B minus A there, and B minus A there, components 1, 2 and 3. Thus, in component form, we can cancel many things out here, and we see that the scalar product of two vectors A and B is equal to multiplication of the three components of each vector and sum them. It's very simple. Okay. We don't need to recall all this definition, but it's useful to have it written down. This is the important result on this slide. So I've got a slide here that's summarising what I've just said, and this is really the one to remember. If you've got two vectors in component form, we'll write the scalar product as A dot B, hence it's called the dot product. The dot comes between the two and ideally slightly above the line, so it's not a full stop. But it doesn't matter if you put a full stop in, but you do need the dot. In component form, this would be A dot B equals those three, and in geometric form, A dot B is equal to magnitude of A times the magnitude of B cos theta, where theta is the angle between the two vectors. This is quite handy if you're doing some geometry, working out angles. That would be very difficult if we weren't working in vectors. The angle between 0 and pi. Some important points about the scalar product. It gives a number, a scalar, hence it's called a scalar product. So the result is a single number. It's a product of two vectors, not scalars, and you must put the dot in, or else it not really defined properly, and you will be confused. So you need to put the dot. So it's called the dot product. Right, so look at some formal mathematical rules. A dot B equals B dot A. That's quite handy. So it's the same rule, same rules as normal arithmetic for order of doing things. Associative law. Now we can't have three vectors. It doesn't work because dotted. Because you dot two vectors and you get a scalar. So A dot B dot C doesn't exist, not defined, because you'd have a scalar times a vector and then you wouldn't be doing a dot product. Distributive law, so expanding brackets. Well, this may be slightly surprising, but we can expand the brackets quite in the same way as normal arithmetic. Distributive law for a vector addition. Similarly, we can expand brackets. Again, maybe quite surprising, but quite handy at times. Okay, this proof of distributive law. Well, let's just go through that again. Not something we need to remember, but we put it in components. It's a bit easier to see. So we expand the components, and we have this expanded bracket. So we see that A dot B equals those. That's by definition, and A dot C is those by definition. That's by definition. Thus, A dot B dot C equals A dot B plus C equals A dot plus A dot C. Okay, again, a proof. You can work through that yourselves. Powers of vectors. Now, A dot A is clearly that, which turns out to be A dot A cos theta. Theta is 0. So A dot A squared is equal to the magnitude of A squared. That's the only power that we can do for vectors, because we can't, because that's a vector of dot products, because we get a scalar, so we can't do a third dot. Okay, that doesn't exist. A dot, A dot, A dot. For unit vectors, this is quite useful. I squared, I dot I is equal to 1, and similarly for J dot J is 1 and K dot K is 1. That's really useful. Perpendicular vectors. So A and B are perpendicular. Theta is equal to pi over 2, 90 degrees. Cos 90 is 0. Thus, if A dot B equals 0, we could say that A and B are at right angles. They're perpendicular. So this is an important result of the scalar product, and it's particularly important when we look at the three axes, because the three axes are perpendicular to each other. So I dot J is going to be equal to J dot K is equal to K dot I, which is all going to equal to 0. Very handy to know whether two vectors are at right angles, or it's very handy to help us find a vector that is at right angles to another one. Scalar product using Cartesian vectors. So we've written a vector out, A, with the components of A. I've used capitals this time, multiplied by the three unit vectors, and B, similarly, components, capital B and components there. We want to show that A dot B is equal to the three components multiplied and summed. And we can just expand this quite simply. Gets a bit long, but we can expand those brackets. Let's have a look what we've got up here. Now we have j dot I, k dot I dot k, j dot k. And what do we know about these? We know that these are 0. So these are all 0. That one too, and that one. And we know that these are 1. So the result is our definition of the scalar product or dot product in component form. Now we said that A dot B equals 0 means that the two vectors are perpendicular, but it's not always the case. Well, first we have to prove that A or B are not 0. Only when A and B are shown to be non-zero are the two vectors at right angles. This may seem trivial, but when you don't actually understand what, or you can't actually visualize the vectors, then you don't know that one of them may be non-zero. So you need to do that check. It's really important. So we can also look at when we've got 3 vectors, if we do A dot B minus C equals 0. Well, what do we know here? Doesn't mean that B is equal to C. We need to show that A could be 0 or B minus C could be perpendicular to A. So there's a little bit of checking to do when you're checking for doing calculations for vectors at right angles to each other, perpendicular to each other. And the implication is here that vectors can't be cancelled out like scalars. We have to do a bit more checking for existence of non-zeros. Let's have a look at an example of perpendicular vectors. So we've got 3 vectors, A, B and C. Show that A dot B equals A dot C and interpret the results. So A dot B, well, we'll just multiply the components and add them. A dot B equals 2, A dot C equals 2. They're equal, which is what we're asked to show. The two scalar products are equal, but it doesn't imply that B equals C. Well, why not? So if we take the difference of B dot A dot B minus A dot C, well, that's equivalent to this bracket, and it equals 0. So the two vectors A and BC, which equal that, are clearly perpendicular and orthogonal, or orthogonal or at right angles to each other. So theta would be 90. That's an important example to be aware of, just understand its implications. Right, let's get back to where we first started, component of vector along another vector. Okay, so we've got F along A. Right, what do we need to do here? Now we've learnt a little bit about vectors and the dot product. Clearly, component of projection of F in the direction of A is F cos theta, magnitude of F cos theta. Using the unit vector along A, remember we write the unit vector with a hat, that's a unit vector in the direction of A, then we can write A hat A is F hat A cos theta, which is the same as F cos theta, what we wanted to start with. So if we have a vector A, then what we need to do is calculate a unit vector, multiply that by the force, and we get the component of the force along A. Just note why we've cancelled the A hat, magnitude of A hat here, because remember it's a unit vector and the magnitude is 1. that can also be rearranged into this form. Let's have a look at the example of the scalar product. Find the angle between two vectors. Well, this is quite trivial, but a typical calculation. Two vectors. Let's take the do the scalar product, the dot product. We've got it in component form. We've got it in Cartesian form. Comes out to be 18. Magnitude of A is root 13. Magnitude of B is root 29, so we've got root 13 times root 29 cos theta equals 18. Trivial to calculate theta. Theta comes out to be 22 degrees. So another example of a scalar product. We've got three vectors here, A, B and C. Find AC, B plus C, dot C and A dot B. So again, quite trivial, but we've got an extra question. What can you say about the vectors A and B? Well, we don't know anything yet, but let's see. So A dot C, we multiply the components. The answer is 5. B plus C, we add each of the components. There's the answer is another vector, 1, 4, 0. A plus B dotted against C, we multiply each of the components and sum them. Answer is 11. A dot B, we multiply each of the components and sum them. The answer is 0. So what do we know about A and B? Well, we can see that A and B are non-zero, so A and B are perpendicular. Again, quite a trivial example, but important to understand what's being said there. Scalar product. Now we're going to look at this idea of scalar product calculating force, component of force along a particular direction and moving along that particular direction to give us the work. So find the work done by a force, and the force here is defined as a vector when it's moving a particle from P to Q, where we know the positions of P and Q. So we're going to need to write a vector PQ first of all. So the vector R, we're going to call this vector, going to be PQ, and it'll be 2 minus 1, 4 minus 2, 4 minus 3, which is 1, 2, 1. So the work done by the force is F dot R. If we can work that out, turns out to be 10. 3 plus 2 plus 5 equals 10. And 10 Newton meters, because we actually were given some units on the vectors. Next example, another scalar product. Find the component of the vector F in the direction I and in the direction of 3, 1, minus 2. So the I direction, we know that's a unit vector. So F dot I gives us 2. Is the vector unit 3, 1, minus 2 a unit vector? Well, we can clearly see that it isn't. We can work that out. It's root 14, so it's not 1. Hence the unit vector in the component of F, which is what we want, is 3, 1, 2, minus 3, 1, minus 2, all divided by root 14. So the component of F along U is F dot U hat, or F dot the unit vector in direction of U, which is minus 2 over root 14. So here's a slightly more sophisticated looking example. It's no more difficult than the last two examples we've got. So we've got this example of a frame like this. The frame is subject to a force 300J, so it's just in the acting in the y-axis direction. Determine the magnitude of the components of this force parallel and perpendicular to the member AB. So AB is here, so we want to have force continued on in that direction. Now we can look at this diagram and we see the components, see the coordinates of A, or essentially the position vector of position vector of B. So the magnitude of the component of F along AB is equal to the dot product of F and the unit vector along AB, which I've labelled here UB. Okay, so the unit vector along B is the vector position of B divided by the magnitude of B. Let's see this in numbers. So RB is 2I, 6J, 3K. So there's the 2, there's the 6, and 3 is the K. So we work out the magnitude, divide it all by the magnitude, and there it is in terms of unit vectors. So F along AB, in the direction of AB, is F dot UB, this unit vector. And that's all just multiplied out, and it comes out to be that the force is of magnitude 257.1 newtons. Now you can see that would be extremely difficult to do if you weren't doing it in vectors. Second part says, can we calculate a perpendicular vector? So we've got F dot AB in unit in components. The perpendicular would be vector would be F minus FAB. So its magnitude can be just determined from this calculation, as we do in normally. Some key points here to remember from all of the slides. A, B, we write A dot B. This is the definition of A dot B in component form. This is a definition in geometric form. We can work out the components of a vector along another vector by using this formula, and we've seen that in several examples.